9, similarity. Back in like Unit 4, we talked about angle-angle similarity and SAS similarity, side-side-side similarity for triangles. But in general, shapes could be rectangles or pentagons. It's something where you were doing proportions if they were similar, and you were looking at scale factors. We're going to do the same thing with 3D shapes. Now, I have 2 examples to lead us in, and I want us to see the relationship between similar figures. So we start us off with a rectangle. It has a length of 2 and a width of 4. And the other side will also be 2 and 4. Another rectangle has a length of 6 and a width of 12. Okay, so, and they're rectangles I could fill in all the right angles. Are the rectangles similar?
Yes.
Oh, by the way, no, we can't use angle-angle similarity. That's only for triangles.
Well, never mind then.
Yeah.
Yes.
But we can. So here's what we're gonna do. Let's look at the scale factors. So let's do this. Let's do this one. The scale factor. Let's just do the overall right over here. Overall scale factor 2 to 6. Well, here I actually have to check and make sure these are the same. 2 to 6 and 4 to 12. Are those the same? They're both going to be 1/3. Now, just as easily, do you remember you could go the other direction, 6 over 2 and 12 over 4? So that the scale factor could have been 3. So I'll put or here. Okay, now, going from the big to small would be 1/3. Going from the small to big would be 3. So are they similar? Yes, they have. They have all congruent angles, all right angles, and then the ratio between the sides is equal. They're 1/3 or 3. Now here's what I want to do. This is something a little bit new I want to look at. Let's compare the perimeter and area. So for this shape, I'm going to do perimeter and area over here, and then for this one, I'll just write it here for this one. Let's look at perimeter first. I'm just going to add them up really quick. 2 plus 2 is 4. 4 is 8. 4 is 12 units. 2 times 4 for the area, so that'd be 8 units squared. Going over to the big rectangle, I add those all up. It's going to be 36 units. I'm going to do the area, 12 times 6. Let's see, so 6 is 72 units squared. Okay, now the reason I did that, I wanted us to look at the relationship between perimeter and area and see if it follows the scale factor. Okay, so how about perimeter? Between this one to that one, does that follow the scale factor? 12 to 36 would be times 3, or this direction would be times a third. So yeah, I'm just going to write perimeter, scale factors, still true. How about the areas though, 8 to 72? Does the scale factor still work there? No. Does anybody see what the relationship is? It's times 9. Now another way to write 9 is taking our scale factor and squaring it. So 3 squared, that 3 was our scale factor. If we take our scale factor and square it, that would have gotten us to here, 9 times 8. So for area, you have to take the scale factor, I'm going to put squared. The scale factor was 3, or 1/3 for both.
Great, so how do you know which one to use? How do you know if you're...
Oh, it just I was going small rectangle to big, so that scale factor was 3, getting bigger. Or if I was going big rectangle to small, it'd be 1/3. So if that was the case, I would have started with 72 and times a third squared, and that would actually equal 8. Just because a third squared is getting smaller. It's 1/9. Let's see. So in a similar way, I'm going to do one with volume in a second. And we're going to see again a similar relationship as that one. Now before I do, I guess I could have thrown this in the top. So we're gonna start looking at 3D shapes now. Any questions on that first one? So perimeters was same scale factor. Area was the scale factor squared. So similar solids, congruent solids, same everything, right? Areas, the same shape and size. Similar solids, same shape but not necessarily the same size. That's a scaled figure. But all the dimensions are the same. So like if it was 2 cylinders, okay, and they're similar, well, the radii have the same ratio, and so do the heights, because that's the main part of the dimensions. And these problems below, they have to tell you that the figures are similar in order to do the relationship up here. Or some figures are always similar, so they wouldn't have to say that they are similar. So for example, I'll give you a 2D shape that's always similar, circles. We found this out a couple units ago. Circles, and it's just depend on a radii, on a radius. So there's only one, just this is 2 and this is 6, just times 3. All circles are similar. And I think what's another shape that's 2D shape that's always, take 2 of them, they're always similar. Square. I don't know the symbol for square, but I'll just put squares like that. All right angles. And again, if this is 2, they're all 2 or something, and these are all 6. That's just times 3. Thank you. And actually, I'm going to generalize it. Actually, any regular polygon. So like, those 2 hexagons are similar. Or if I took 2 octagons, or 2 decagons, 2 pentagons, as long as they're regular,
Let's finish it. Just finish
then
it.
as long as they're regular, then they're going to be similar. So let me just generalize that. Regular polygons. Okay, now that's for 2D. Hey guys, what we can do for 3D, it's the same shapes, but 3D versions of each of those. So like, it's a circle, sphere, right? Any two spheres, which is just based on a radius. And then, 3D version of square, any 2 cubes. Oh, here, I can make it here. Just turn these into cubes. And it's just times 3 still.
A very long cube.
Well, you're right, you're right. I'm sorry.
It's not to scale, not to scale.
Yeah.
Put that on the
Picture not drawn to scale.
I hate
I
this.
thought it was a top judgment.
Thank you. And then regular polygons in 3D are the Platonic solids. If you remember, there's the regular polyhedron. Polyhedron. Polygon was 2D shape made of line segments. Polyhedron was a 3D shape made of polygons. Polygons.
No.
Yeah. I'll show you. It was this. Like that's made of all squares. That's made of all equilateral triangles.
Whoa. Octahedron.
Yes. Okay. So let's do another example. So that's it for if they say, oh, here's 2 cubes. They don't have to say they're similar. We already know they're similar. All right. I'm gonna do one more example with it's the same as the one above, but it's 3-dimensional. So we're going to compare the volumes in this one. So in this one, we'll figure out if the solids are similar, and then we're going to figure out the scale factor, and same as about ratio of the areas and volumes. All right, so I've got 2 prisms. So 2 prisms, not always similar, but let's check. Let's see. I'm going to do a ratio here, 5 to 2. Or you can do 2/5, whatever in order, stay consistent. 15 to 6, and then 20 to 8. Now, just looking at them, I don't know if they're all the same, but just put them in your calculator and make sure that they're all the same, and they are. They're all 5 1/2, 2.5. Go back here, so that's the, yes, they're similar. Scale factor, 2.5. You could write it as a fraction, 5 halves. If you were going small to big, it would be 2/5 or 0.4. Okay, so I'm just going to write it at, well, let me write it, I'll write 2.5. As a fraction, I'll just put it in parentheses, fraction within 5 halves. Okay, now based on the last one up here, remember how we said to get the areas, it'll be the scale factor, but you have to square it. I want to show you it works on this one too. It works for anything with an area. Surface area, area of just a face. No, we haven't been doing surface area, so let me tell you. Let me tell you what you would get when you find the surface area of this one. The big one, it would be 950, and the small one, it would be 152. And when I do that ratio, it would be 950 over 152. Which is 6.25. To show you that it works, that last thing with the area, I take my scale factor and square it, and guess what? It's 6.25. So showing you the same thing with the rectangle holds true. So what did I say it was? It was 950 over 152. 6.25. As a fraction, would have been 25 over 4. So basically, guys, you take this number, you should go back, you square it, either one of these versions, and you would get this one. That's the ratio of any area, surface area, area of one face. Now, before we do it, what do you think is going to happen with the ratios of volumes? Any guesses? Yeah. Scale factor. Go back to that, and you cube it. Volumes cube units. You cube it, and that's going to be a ratio of the volumes. Yeah. I want to show you up here, since we have some numbers, we can actually do it. The volume of the big figure, that's a prism, capital B times H, but because it's rectangular, you do length times width times height. 5 times 15 times 20. 1500. For the small prism, 2 times 6 times 8, and we get 96. So this time, if I do a ratio, 1500 over the 96, let's try it out here. 96, there we go. 15.625, let's verify that scale factor cube. There we go. So now normally you wouldn't have to do that work of finding the volumes. I was just showing you for this one. So you take that scale factor, you cube it, that's the ratio. So as a fraction, it would have been 125 over 8. So if you want to make a note about how here we squared it, and from here down to here we cubed it, the next theorem at the bottom sums it up. But if you want to make a note about that, you can. So let me sum up the theorem, and then see if there's any questions, and then we'll try just a few more examples. So at the bottom, it just says, when you have two similar figures, okay, so you're scaling one. Oops. Just down there, we go. Two similar figures, you scale one by a factor of k. Now, k is was what I'm going to refer to as the scale factor. So it could be as above, it could be, you could write it as a decimal, like 2.5. You could write it as a fraction, it could be like 1/2. Okay, but some number, k is a number, it's a scale factor. Well, then what we know, anything lengths, widths, or perimeters, here, lengths, areas, and volumes, is they are multiplied by k. that's the lengths multiplied by perimeter, k. Areas, k squared. And volumes is k cubed. I wrote it on the next one, similarity transformation. So if you, here's one shape, one cylinder or something, scale it to this one. This is a similarity transformation to transfer this one onto here. We did that with 2D shapes. We could do it with 3D shapes. Now, I used to use it. I wanted to show you that. I used to use this as a scale factor. I used to always write it as a fraction. I like using k more because it represents any number. But this is just the form if you want to write it as everything as a fraction. So if you want your scale factor to be 1/2 instead of 0.5, it's exactly the same as k. I just made it two numbers, one on top and one on bottom. Same thing works. All right, so any thoughts before we try a few examples with theorems? Okay, let's try a few. Let's flip to the next page. I'm not going to do all of them, but I will do several, kind of jump around a little bit here. Okay, I got two cylinders. Cylinder A has a radius of 2 and a height of 7. Cylinder B has a radius of 6 and a height of 21. Certainly bigger. Are the figures similar? Well, let's check the ratios. And we can kind of see, right, the radii here, 2 to 6 and 7 to 21. Is that the same ratio? Times 3. So, yeah, scale factor is 3 or a third. 2/6, well, or 6/2, I guess. And 21/7 are both 3, or you can reverse it, do 1/3. So here's kind of a newer question based on what we know now with the theorem. Suppose you didn't know anything about this, and I said, or even this, just that they're similar. Cylinder A has a volume of 28 pi. Using our theorem from before, and not a volume formula, let's just say all we know is 28 pi. Find the volume of cylinder B. So what we can do is, since it's scaled, and they're similar, I can use this theorem from before. So our scale factor is 3. I take the 28 pi for A, and I want to go here to here. But I'm not just multiplying by 3 because that's the scale factor. Right? It's volume, so I have to multiply by 3 cubed. If it was something with area, surface area, I would do 3 squared. It's as simple as that.
Those two in terms of
Yeah. So this is 27 times 28, 756 pi. So that's just an example right there showing you, all right, take your scale factor, sure, but you're not multiplying by 3 because it's volume. Multiply by 3 cubed, k cubed.
Oh, what's that one?
This one,
Yeah.
756 pi. I'm going to skip the next one. Any other questions on this one? Let's do these two. These are quick. They're just asking for a ratio. This one's going to ask for the ratio of the volumes. This one asks for the scale factor ratio. All right, so this one says 2 cubes have sides of 9 and 21. Now, they didn't say they're similar. This is where we say, oh, any 2 cubes are similar. That's one of the shapes that are always similar. So they're similar. 2 cubes have side lengths of 9 and 21. I don't have to draw a picture. I'm just showing you 9 and 21. Find the ratio of the volumes. Well, what we can get is k. Okay. Again, I'm writing k now for like scale factor. So k, I can get that ratio. You want to use 9 to 21 or 21 to 9?
921.
9 to 21. scale factor or ratio? Ratio of the volumes? Cubit.
Do you simplify it or
Oh, you saying the 9 to 21?
not?
Yeah, I guess you're right. We could have simplified 9 to 21 first. Yeah, yeah, you can. Yeah, it doesn't matter. We can reduce later. You want me to reduce it?
Yeah.
So this is really divide by 3, it'd be 3 sevenths. Yeah, 3 sevenths. So cubit, and we get 3 cubed is 27. 7 cubed, 43. So that's k cubed. Here, I should even write it here. K. You see, oh, we're cubing it. That's the ratio of the volumes. K cubed is the ratio of volumes. So kind of the only difference between that and the first one was written as a fraction. So I wanted you to see that. Still the same thing, just
Wait, how did
fraction.
you get 27 on 3/4?
Just cube 3 and 7. Yeah, if you do a decimal, if you do 3 sevenths cubed, the calculator might give you a decimal version. I just did 3. I did 3 cubed and then 7 cubed. I think that's reduced. Yeah. Let's do another quick one like this. 2 similar prisms, right there somewhere, have surface areas 144 to 324. Area. So what I can write with, so what can I write with that? Area. I can write k squared. Again, k squared represents the ratio of the areas. So let's do that. So I'm going to do 144, 324. Again, we could write 324 over 144. The order wouldn't matter. That's what I know. Now they want the scale factor, k. But again, k is the scale factor. So what do I need to do to this to get back to the scale factor? I mean, think of it, this is why I write k squared, k cubed. I need to do square root if I want to get to k. So k, my scale factor, is just the square root. By the way, you could have reduced this one again first, 144 and 324. Well, it would have been 4 ninths. Like if you divide, if you reduce this as a fraction, it would have been 4 ninths. First, I'm saying, yeah. Then it doesn't matter if you want to do that first. Then the square root would have been 2/3. If we just do the square root here, it would be 12 over 18.
Simplify that to 2/3.
And then you could simplify it to
Well, not
2/3.
the calculator.
What says
Wait,
0.6?
why
by the
would
way?
you-
What? Did you say that? Okay. So 2/3 is the best answer on that one. Yeah.
So 4 ninths would be what you would get if you simplified 144.
Yes. This is,
Oh, okay.
so like without doing a square root, you get 4 ninths first. Then you could do, that's still k squared. Then you could do a square root. The best answer is 2/3. And really, that's fine. But this is a simplified version. All right. Any thoughts on those two? Oh, yeah.
Wait, so is K the surface area?
No, k is scale factor. K squared is a ratio of the areas.
So just K is still.
Yeah.
Oh.
That's what the state uses as their variable for scale factor moving forward. And I like it. It's just easy. K and k squared, k cubed.
Oh, and then like K squared would be like K.
Yes. Right.
Do you know
Sure.
okay is universal? Like
I'm sorry?
okay, the word okay, it's like the universal.
Oh,
thing.
did not know that. No.
Yeah, I didn't either till Spanish last period.
Well, guys, let me skip the next example. I don't know if I'll have time to come back to it. I want to do one on the next page, though, for sure. Let's do this. They're both the same idea, so I'm only going to do one. Let's do the bottom one. The volumes of 2 similar figures are given.
I'm making cubes.
I was going to say, it doesn't tell us which, so they're similar. That's what matters. You can make it cubes, prisms. I mean, there's no pi, so it's probably not like cylinders. But
Look at that, perfect.
Okay, in any case, here, these are two volumes for similar figures. We also have a surface area of the smaller figure. It's going to match up with the 6 cubic centimeter volume. Find the surface area of the larger figure. And along the way, we'll get two other things. We'll get the scale factor and the ratio of the areas. That's supposed to say 1. Okay, so let's write what we would know. Here's what I like to do on these types. I like to write the full chart, because we're actually going to need all 3. Scale factor, ratio of areas, ratio of volumes. The only one I have right now is volumes. So yeah, so I'm going to write that as k cubed, and I can write a ratio of the volumes. Again, it doesn't matter if I do 384 over 6 or 6 over 384. Let's reduce that. You really don't have to. It's going to make it a little easier though. I can divide this by 6 and get 1, and divide 384 by 6. I can't forget.
64.
64. Thank you. So that's still the ratio of the volumes. Now, what we want, so that is, oh, I didn't get into this yet. So that is still the ratio of the volumes. I want the surface area. So I want to go to k squared. I need k by, there's no good, there is, but do you want to know it till next year? So yeah, so let's go to k first, the scale factor, and then we'll go to k squared. So we're going to get k next, so I'm going to do a cube root. Cube root of 1 is 1. And the cube root is 64. If you don't remember, it's math 4. And so, yeah, cube root of 64 is going to be 4.
And then you square it to get that.
Yeah. So that is scale factor. I just answered number 2 up here that I looked the scale factor, the 4th, or 4. 4 over 1 or 1 over 4. And then, yep, we just, now we square it. So again, there's never a good way to go directly between the area and volume, k squared and k cubed, those ratios. So if you need the other one, go to k first, and then go to the area. So now I'm going to go to k squared, so I'm going to square it. 1 squared is 1, 4 squared is 16. And so I just answered part 3 here. Ratio of the areas is 1 over 16. Okay, now integration of the volumes is 1 over 64. We already have that. So now let's answer the question, find the surface area of the larger figure. Okay, so I go back to this one. Now, I'm going to do a proportion to finish solving this one. One ratio I know between the areas is this one. 1 over 16. That was a ratio of the areas. I'll set equal to. Yeah, now 6 is this. The surface area is small. That's the smaller one. So that's definitely, that's a smaller surface area. So that's going with the 1. So sometimes is it 6 go up top or on bottom? It goes up top because that's with the 1. Smaller. Find the surface area of the larger figure. I'm going to call it x, and that goes on the bottom. And then we cross multiply. Yeah.
Wait, so why is 1 over 16 a proportions?
Well, this is just the one ratio in the proportion, and it's from this. This is the ratio of the areas. That's why I chose to use this one.
How's it the ratio of areas?
That's the k squared is. It's the ratio of the areas. Now, it's just the ratio, but then they give us the actual surface area. And so I can use that ratio, 1 over 16, to then find the missing.
Oh, and then like k cubed is like ratio of the volume?
Yeah.
Oh.
Yep, so 1 times x is x, and 16 times 6 is 96. Cubic or sorry, squared 76. So see, even though we haven't done any, and I'm not going to ask you to actually compute surface area, like a formula, but what we can do is use our knowledge of similarity to find that one. Now, real quick, most common error I see on this one is students will set up a proportion like this, which is great, but they either use 1/4, they got the scale factor and did that, which you can't do, or they'll use 1 to 64, or even 6 to 384, or non-reduced version. you got to get the right ratio. Is it scale factor? Is it area? Or is it volume? Well, this is area, so we got to use the 16. There we go. The 1/16. Okay. Questions, Lana?